In listen-only mode.
Hey guys, well, good afternoon, good morning, good evening, wherever you are in the world. I'm Mike Aubrey, and with me, my partners in crime here, Princess Leah Pandolfi, and then our special guest today, Joe Foster. Joe, thank you very much for taking the time to be with us today.
Oh, my pleasure. Happy to be here.
So, our topic today, photovoltaics. This is an interesting one because, as you guys know, as contestants, we're judged by how long we stay in the air. And so, if there are ways to make it so that we can stay in the air longer by acquiring energy along the way, or if there are ways to help us with our mobility to make it so you can power from anywhere. Photovoltaics offer a lot of interesting enabling technology that's definitely worth exploring. Hence why we're having the webinar today. So I want to introduce Joe. Joe, he's what we call a solar technologist, and so he's got 7 years of experience with that. Along with that, he's a lifelong enthusiast in RCs and various other flying objects. He actually has experience working with UAVs for both civilians and military uses. So he's a and now he works for a fruit company down in the Bay Area. They sell electronics. You might have heard of them. But I'll let Joe give his own introduction. Joe, thank you so much for being with us today, and we're really looking forward to learn from you. Thank you.
No, thanks so much for having me, and it's my pleasure to share what I know about PV materials for these kinds of applications, and hopefully help the group in general. So, should I go ahead and share my screen? You have it
I,
there.
I think, yeah, I can see it. I'm seeing PV primer, and then yeah, we're going.
So,
Let's do
okay,
this.
good. So, please, so I guess the format again is questions at the end, or just you'll raise a
Yeah,
hand here if you need me to stop.
absolutely.
Hey,
Yeah,
hey
go ahead,
Joe.
and we're going to be watching the chats.
Joe, before you get started, do you mind kind of like talking a little bit more in detail about your background?
Sure, happy to. I'm a technologist, a business development specialist. Over the last 15 years, been focused in that area and business development, primarily raising equity for technology startups. Prior to that, I spent about 12 years in a business that I had built with several other partners. A several $100 million per year venture, a couple thousand people around the world. And I was the chief technology officer and senior vice president of business development for that company. And we were engaged in doing a lot of M&A work. So my background is mostly in business building, raising equity, mergers and acquisitions, been part of 15 M&A deals. And most recently was at Alta Devices, which is a thin film gallium arsenide solar cell startup, and company's now in its sixth year. Um, we raised about $150 million of investor equity to commercialize a nascent technology in thin film gallium arsenide, which I'll show you in a little bit, is to date the highest efficiency solar cell yet produced by man. And it has been used primarily in the space program because of its extraordinary energy density. But what Alta did was take a technology that was really built for space and the rugged requirements of space and create a thin film, flexible material of ultra lightweight with very high efficiency. And so I'm going to cover in this presentation all these materials, show you a comparison of them, and really try to focus in on the practical application of commercially available solar materials and some of the things that you should consider when you're trying to identify a material for these applications. And then, how can they integrate into the system? Because at the end of the day, you have to have, a system that is robust to the task. And I'll try to lend my insights into some of those challenges. And so again, just closing on my background, I have a bachelor's in mechanical engineering. I've got an MBA, both from schools here in California. I'm 25 years here, born and bred in Silicon Valley. I've got a family of 3 daughters. My oldest in her second year of college. I've been in technology since I was a baby. My dad worked in Silicon Valley here for 40 years for 2 companies, very high-tech companies in defense. And so kind of just been immersed in technology since I was a kid. My wife and I both were born and raised here. We grew up in the same neighborhood. Her father worked for a semiconductor company that built some of the first video game controllers for Atari. And so, at the age of 7, 8 years old, I was, handling the first prototype video game. So I feel like, you know, technology is in my blood and in my DNA. And, you know, now I work here in Cupertino at Apple Computer, working on next generation technologies for consumer electronics. So on to PV. And so this is more of a PV primer. You know, there's some technical content in here. There's lots of assessments and opinions. So I just kind of caveat it in that way. But I'd be happy to take any of this conversation offline and go deep technically as I'm capable for any of the members here. So just to start, if we're trying to identify a PV material for UAV applications, probably the #1 challenge is how to integrate it. How do you get it onto an airframe and do it in a way that preserves the flight worthiness of the aircraft? And that, you know, implies lots of things. That implies aerodynamics. That implies, you know, energy to weight and power to weight kinds of contributions from a technology like this, and whether or not they can make a meaningful benefit to whatever the mission profile is for that aircraft. And so, you know, in my view, you know, having designed and built lots of aircraft, I always want it to be lightweight. I want whatever I'm going to apply that's in addition to the aircraft itself to be thin and flexible and largely conformal, and really to preserve any aerodynamic properties that you have for that particular aircraft. And you know, that the criticality of that changes with, you know, the flight regime for these kinds of aircraft and their size, obviously. Really, you want the highest energy generation material. You want something that's going to preserve the attributes of the two points above, but also provide the highest amount of energy in the real-world condition. And the real-world condition here is what's important. And I'll talk a little bit about this later. Solar cells are generally identified by efficiency, and that efficiency is always measured at what is known as a standard test condition, or STC. And that standard test condition is basically 25 degrees C in temperature and 1,000 watts per meter squared of irradiance. And it's of a radiance of a solar spectra or a spectra of light that sort of emulates the spectra of the sun. And so when in reality is, we never see those conditions ever in the real world. It's never precisely 1,000 watts per meter squared outside of that particular spectra ever at that particular temperature. It would just be by pure luck that you would run across that condition in the real world. And so we have to deal with the fact that in the real world, conditions will vary. And we'll talk a little bit about that in a few minutes. To kind of go deeper into some of the integration challenges, you know, you need to make sure that you're covering enough area to be meaningful. So some of these aircraft, you know, they might be so small or of a configuration where they don't have enough flat surface to really provide a meaningful amount of power generation. And so we have to be cognizant of that when we're deciding whether or not solar is a good candidate for an airframe. We want it to be compatible. We want to minimize the amount of additional material that we have to add to the aircraft, ultimately trying to minimize the weight. And we want to try to minimize the system integration challenges related to interconnect and also to structural. And so some materials are going to take issue with being flexed and bent. And so, you know, we want to make sure we're putting the solar materials in places where we're minimizing the need to add more structure to the airframe. And we could talk a little bit about some of those details. And ultimately, you're trying to match the solution to the mission. And often the mission is driven by the budget. And so you know, what I try to do in the comparison to follow is really just identify the relative cost of each of these material systems as you consider them. With regard to form factor, obviously lightweight is the most important thing. The single greatest thing that degrades aircraft performance, particularly aircraft in these, like, you know, sub 10-meter wingspan, is going to be weight. You know, the wing loading, if you will, on these aircraft is what is ultimately going to determine, you know, how well they perform in flight, at what speed they need to fly at, how much energy they're going to consume in flight. And so it's certainly lighter, going to consume a lot less energy, just simple lift dynamics. And so, we want to find a solution and find ways to integrate the material and identify material that's really lightweight, which ultimately implies very thin. And very thin is also beneficial to maintaining aerodynamic design practice. So we really are biased toward things that are thin and lightweight, and when you start to apply that constraint to the choices, you'll see the field gets pretty narrow pretty quickly, and I'll show you a chart which identifies that. And then obviously being flexible and conformal is critically important. So a couple of words about solar materials and how we compare them before I'll show you just a comparison of the leading solar candidates for these kinds of applications. We always talk about energy produced, and energy is different than power, obviously, in that power is an instantaneous measurement of how much is being produced, generally expressed in watts. And energy is how much power you're able to produce over time. And that's what's important to these applications. And what we need to know then is, well, what's the energy profile, the energy consumption profile of the aircraft and in its task when it's on its mission. And once we know that, then we can assess how a technology like solar can improve the duration of a flight, for example, by being able to provide energy over time that is meaningful to that task. Now, it's important that it's in time in that, there's 24 hours in a day, and the sun doesn't shine, all hours of the day, and so that becomes a consideration. I'll try to address that a little later. I'm talking about some of the efforts that have been put forth to date, both manned and unmanned, in integrating these materials, and I'll tell you a little bit about what I know about some of those efforts. So, energy produced, we're really looking at kilowatt hours. How many watt hours of power, of energy am I going to be able to produce with that solar material? And it's in a varying solar resource. So, obviously, the sun is moving in position during the day. The amount of atmosphere that the photons need to travel through to get to your eye and to get to the solar panel changes throughout the day, which changes the spectral distribution of light, which photons are actually reaching the target, which spectra of light is really being seen. It also affects the intensity of the light, or what's known as the irradiance, which is generally expressed in watts per meter squared. There's a figure of merit, which is it's a number 1362. 1362 is the average amount of power that hits the Earth's surface per day per square meter on the planet. And so, there's the solar resource that's available to us in direct sunlight sort of varies between 900 watts per meter squared and 1300 watts per meter squared, given all the other factors. And so this is the range that we consider as kind of what is the available energy. And so what we're trying to do with solar is collect some fraction of that. And that fraction is a function of how efficient the material is at collecting that spectra, that irradiance level of light. And so solar materials in general, they respond differently to varying light conditions. And the factors that affect how they respond are things like the band gap for the cell, which is what spectra of light, what range of light spectra is the cell able to absorb, say from ultraviolet out to infrared. Not all solar cells can collect that entire spectra. Some do really well in more the blue shift toward the ultraviolet. Some do much better in light that's shifted more toward the red or to the infrared. And so, that's not a big consideration here in these applications, because really we're trying to find kind of the most utilitarian device for aircraft, because aircraft fly all over the planet and all over the place. But it is a factor when looking at various materials when you're trying to really dial them in for a specific application. And then system efficiency is what ultimately is important. Solar cell efficiency is important because it helps us collect the greatest amount of the available solar resource. But ultimately, we have to take that energy and we have to put it in a form where it can be either used by an electric motor or part of the subsystem of the aircraft, or charging a battery. And so the choice of components that support those tasks become very important. And they're generally a function of how the solar array is configured. And largely the choices on what components to choose are driven by the array that you've designed and what it can produce electrically. So the generation is ultimately what we're going to be comparing with regard to solar cells. Now, to look at a quick comparison then, just in an eye chart form here, there are a number of technologies that I would consider currently are mainstream, meaning they have scaled sufficiently to be economic for kind of commercial solar applications, meaning residential, commercial rooftops, and utility scale solar fields can all be addressed by the technologies that are in this kind of mainstream category, and I've listed 5 of them here. 3 of them are based on silicon. The other 2 are known as thin film technologies, and they are basically thin layers of semiconductor material that are either grown or deposited onto a substrate. Now, the crystalline silicon are these kind of square, roughly 6-inch square, 6-inch on a side silicon wafers that you see on every solar panel sold at Home Depot and Lowe's and wherever else, and mostly what you'll find on people's rooftops. There are several kinds of crystalline silicon. Monocrystalline silicon, which is of a single crystalline structure. It is the most efficient silicon solar cell yet produced. Companies like SunPower produce these devices. They have the form that they take is rigid. They're wafer-based, and silicon wafers are very brittle. And so you have to be very careful in how you handle them. This is largely why they're encapsulated in glass on rooftops. It is to maintain the structural integrity of the material. And largely those applications require 25-year life, and so they need to be ruggedized for environmental stresses through 25 years worth of service. And so now that's not our application. We're measuring our performance or reliability probably in days or months and not in years. But still, we have to deal with the fact that the materials are brittle and that they can be prone to cracking. So crystalline silicon is largely the choice of material that goes on folks' rooftops. It's the cheapest material today. Solar panels, the full panel, which includes the cells, all the encapsulants, the integration materials, the junction boxes and cables. You could buy a solar panel for, at $1 a watt, for a panel today, and typical panels between, a couple hundred watts, 250 watts, something like that. So a panel of that size can be purchased ready to plug in for around, $1 a watt commercially today. But it has its limitations. If in these applications it doesn't work, and so we have to find ways to make these cells flexible and thin. And so there are efforts that have been put forth to date, largely by SunPower, to produce really thin monocrystalline cells. And the thinnest they've been able to produce to date is 130 microns. And these cells are flexible in that they can be bent moderately. And there's a good example in the public domain of an aircraft that uses these, the Solar Impulse aircraft, which many of you are familiar with, I'm sure. It's a manned aircraft that flies under battery power, and it's proven that it can sustain continuous flight for over 24 hours using the combination of energy produced by the sun, stored in a battery, and then consumed at night, and then generation over the course of the next day supports the next night's flight. They've used these cells successfully in a large aircraft, and they work well in large aircraft because the bend radius of the surfaces is very gentle. In an aircraft that's got a 300-foot wingspan and a 10 or 15-foot chord, and so the challenge of flexibility isn't so acute in a large airframe. As the aircraft gets smaller, and certainly when you get sub 10 meter, the bend radius are getting tighter than you could accommodate generally with crystalline silicon. And so the compromise then is I can't cover surfaces that are curved. I can cover large, gently curved surfaces, but I can't cover radically curved surfaces and take advantage of the surface area to collect energy there. So that's been the drawback largely for solar, has been the availability of materials that can accommodate the need to be bendable, flexible, and lightweight. And largely the materials that have been available have been crystalline silicon. Now there is a thin film version of crystalline silicon, which I've noted there. It's called amorphous silicon, and it's denoted as A-SI, or amorphous silicon. And it is a material that is also silicon. It's not monocrystalline. It's amorphous. It's a random crystal structure, and because of that, it has much lower efficiency. The best cells produced to date are about 12%. So I'm giving them the benefit commercially. Commercially available amorphous silicons are really about 10%. But if we look at really efficient cells, well crafted, you could probably get to 12%. And the cells are much thinner, 60 microns. However, you still are generating a modest amount of power. 12% efficiency when you put it on an aircraft of a couple meter wingspan is only going to yield about 50 or 60 watts of power. And then, is that really useful or not? That's the challenge. These materials are generally a little bit heavier in that they are on a metal foil of a couple mils in thickness, and so that has some weight to it. And so when you look at the power density, you can get to about 320 or so watts per kilogram using thin film amorphous silicon. Over the last 10 years, a lot of research has been done in developing other kinds of thin film solar cells that would have much better efficiency. And the one of most recently that has gained a lot of traction over the last 7 or 8 years in terms of investment, and now is starting to become mainstream in terms of its commercial viability, is CIGS, which is copper indium gallium diselenide. And I worked for a thin film SIGS company for a year, a company by the name of Solar Power. So I know a little bit about how this material performs and its attributes. The efficiency of SIGS can be as high as 19%, so it's really approaching the efficiency of crystalline silicon, and we expect that it would be on par with polycrystalline silicon, which is not monocrystalline obviously, but it's slightly lower efficiency, and it's denoted as the P-silicon above. But today it's commercially available at about 15%. It can be flexible. It's a very thin film, about 60 microns in thickness. It's also on a metal foil, just like amorphous silicon. So the weight itself per square meter is about the same, but the efficiency gives you a slightly better power density of about 400 watts per kilogram. Now, SIGS is a candidate for these UAVs, along with the amorphous silicon, for applications that could support that power density and ultimately that energy density. And I tried to give you a figure of merit here with regard to energy density, and I know I haven't spoken at all about that second column labeled specific generation. I'm going to circle back to that in just a minute. But what I'll tell you what that factor is. That's the amount of energy that you would expect to collect on a per watt rated basis. So earlier I said that all these materials, their efficiency is measured at standard test condition, which is this 25 degrees C, 1,000 watt per meter squared irradiance. The specific generation, in this case, I picked a location in California, and I looked at the NREL data. The NREL is the National Renewable Energy Lab. If you're curious about solar or unconventional energy sources in general, go to the NREL website. You will learn a tremendous amount in the resources that they have online there. One of the topics they'll expose you to is specific generation, and this is a measure. It's a metric used to determine how much energy will I actually collect in a given solar resource, based on the watt rating of the panel, relative to what the manufacturer tells me its efficiency is. And so in this case, I picked a coastal city in California, Santa Maria, and looked at the irradiance profile, the actual spectral distribution of light in that region, collected over 25 years. And NREL has weather sites all over the world that have collected this data, so you can determine the solar resource to be expected in any location in the world today, which is why many of these large commercial solar projects are really starting to reach a tipping point economically, is because we're finding the places where solar resources better than other regions, and there are microclimates and things that affect that. And so what I did is I picked a real location, a real world solar condition, and was able to look at the specific generation. So how much energy would be collected per kilowatt rated, and that's the figure of merit. And this is the number that we compare really to determine, how much energy can be collected for each of these unique materials. And I'll go a little deeper into this metric later, but this is a very important metric for determining the real-world performance of the solar material, not just assessing its performance in a standard test condition in a factory somewhere, which we never see that condition in the real world. So just continuing then, so the SIGS material is now coming into the mainstream. Its cost is modestly more expensive ultimately than crystalline silicon. But again, if you can live with the performance, that you get for the 400 watts per kilogram and the 60 microns of thickness on a metal foil, and that can be integrated in aircraft, if that produces a meaningful benefit, then this material is a good choice because it's very low cost and it has, reasonably good performance in terms of energy collection. However, we find, or at least my experience has been, that you want more energy. 400 watts per kilogram is not enough to get you excited about putting it and going to the task of putting it on an aircraft. You'd rather just add more payload, put more battery, and solve the problem that way. And so, really, for me, the tipping point for making solar useful, and just looking at energy density or power density, is somewhere north of 1,000 watts per kilogram. And just kind of anecdotally, I'll tell you, on like a 2.5 meter wingspan aircraft, you can get about 130 or 140 watts of solar at that energy density onto an aircraft. And when you look at a 2.5 meter wingspan airplane, weighing in at 30, 40, 50, 60 ounces, 125 or 130 watts of power is a meaningful amount of power. That would support generally the cruise mode power for aircraft of that size, carrying a modest payload. And so now you can see energy densities that are going to allow you to fly continuously as long as the sun is shining. And so for me, that seems like a meaningful result. And so at least in our work at Alta, that became sort of a tipping point, performance point that allowed us to really look at addressing some of these UAV challenges. And so, the emerging technology is really focused on a class of materials that are known as the 3-5 semiconductors, and they're elements of group 3 and group 5 from the periodic table. They're largely the same materials that are used to make things like LEDs and laser diodes, and they are largely materials that are known to be high performance materials from this group of elements. And gallium arsenide is one of these materials that's been long known to be an excellent solar material, really an ideal solar material for a number of reasons. Its thermal performance is extraordinary. It has the lowest power loss with temperature properties of any solar material, just a fraction of crystalline silicon. And I'll talk about that in a second. It has a band gap, or its ability to collect the spectra of light, that's wider than any of the other candidate materials. So it's going to collect more of the available solar resource across the varying spectra of light. And then just generally, it does a better job of converting photons to electrons because it is monocrystalline, and it is a direct bandgap material, meaning it is able to more directly convert photons to electrons. Therefore, a higher percentage of them are going to successfully be converted, and fewer of those photons are going to be converted to wasted energy in the form of heat. And so generally, gallium arsenide materials will run cooler than their counterpart materials because they're much more efficient at converting light. And it's a meaningful amount, and normally a crystalline silicon solar cell sitting up in direct sunlight will reach about 45 or 50 degrees C. A gallium arsenide solar cell will run about 10 degrees cooler. And so there are certain applications where that becomes a very important factor. Now there are different kinds of gallium arsenide thin film solar cells are unique in that you can create multi-junction devices which are generally going each of the junctions, and basically it's a single junction solar cell is going to collect a wide spectra of light, the wide bandgap device. When you start going to multiple junctions, you create junctions that are more narrowly focused on a particular spectra of light, and they'll do a better job of collecting more of that light. And then you stack them on top of each other so that you can collect the entire spectra of light and do it more efficiently, meaning increase the overall energy collection of the device. And so what we developed at Alta was a way to create these very thin single junction and dual junction solar cells, and had demonstrated commercial efficiencies in the single junction case of almost 29%. And some of the examples I'll show you later that are public domain, we're using 25% devices. And those we could produce pretty much commercially all day long. And then we had pioneered a two-junction device that was nearly 31% efficiency, which the company believes can commercialize at 30%. And so you could see that there's a pathway now to increasing solar cell efficiencies dramatically and delivering properties that are much better for the application than had previously been devised. Solar cell efficiencies have been moving in the crystalline silicon space at 0.1% per year for the last 10 years, and most of the major advances happened 10 or 15 years ago. And so the technology is very mature. But what you find is these thin film devices have just all this technology runway in front of them, and there's really line of sight to multi-junction solar cells that could have 40 or 50% efficiency. And so these devices then become really interesting for all kinds of mobile applications. Anywhere you have a battery and the need and some flat space and access to light, you could start to collect and harvest that energy. And that includes low light conditions like indoors and in shadowed areas and things like that. And so you could start to see how these solar materials can really migrate into all kinds of commercial applications, including things like the Internet of Things, where you have all these devices with radios and batteries that have a persistent need to be charged. Highly efficient solar cells can collect small amounts of light and keep those devices charged. And so that's kind of the future of where these emerging technologies will go. As their cost comes down, they'll be able to kind of pick off the competitors in the mainstream and the more conventional commercial applications. But almost immediately they'll be useful in the applications that you guys are pursuing, and a whole range of other applications that require persistent charging of batteries in a place where you have access to sunlight. And again, the real challenge I think today with these materials is their availability. There are only a few companies that are endeavoring to produce thin film, high efficiency devices today. And I tried to represent what some of the costs might look like if you were trying to procure those commercially today in the market. And so the punchline here is choices are limited for practical implementation of solar, in my view, on these kinds of aircraft, largely because the size of the aircraft doesn't support the use of the integration of the material, because the material is not flexible enough, it's too brittle or prone to cracking, or doesn't provide enough energy in the application to be meaningful. But hope is there, and there are a set of emerging materials that are largely proven in space and just now being applied to these terrestrial applications because they can be made very thin and retain the performance of the space-based cells. And making them thin is important because by making them thin, you can dramatically reduce the cost. A space-based solar cell that's 30% efficient is going to cost you $250 a watt. And that's because it's built on a wafer that's 125 or 130 microns thick. And you have to bear the cost of all of that expensive gallium arsenide. But if you can make it very thin, of just a couple microns, and in fact the solar cells that I'm identifying here, that 30 micron thickness, only one micron is the actual solar cell. The rest of it is support structure for that device, the metal contacts both on the front and the back, and then a thin polymer that backs the solar cell so it could be flexible. So the solar material itself is just 1 micron thick. So we're using just a very minute amount of expensive material here in making these thin film cells, which is why now they can be cost effective for these terrestrial and commercial applications. Okay, so that's more or less an overview of the landscape of materials. I'm just going to summarize
Hey,
a quick.
Joe,
Yeah, please.
hey, Joe, what are the delineation between the J's? 1J, 2J, 3J?
So a single J, that denotes junction. So there's a single junction solar cell. And so that's the same kind of configuration that you see for all of the devices listed above. All of the commercially available solar cells today are single junction solar cells, meaning there's just one PN junction in the cell that's going to convert light photons into electrons. Okay. Now in a two junction, there's two solar cells that are essentially stacked on top of each other, and it's done so at the atomic level. So it's finessed into the design of the device. But the two junction means that there are two different buckets of light that I'm going to focus on collecting, and I'm going to optimize the solar cell for each of those buckets of light. And the bucket of light is the spectrum or the band gap of light that I'm trying to collect, and that spans from the ultraviolet to the near infrared or into the infrared. And so what I do is I split that bucket up, that solar resource up, and I'm going to design a solar cell that's more geared toward the UV end, and then I'm going to design one that's more geared toward the infrared end, and I'm going to have them work as a single device to collect all of that light. That's what a two-junction device does. A three-junction just splits that bucket of light up into 3 different buckets and attempts to make 3 solar cells together to collect all that light simultaneously and do it more efficiently. And so, theoretically, you could have many junctions where each of those solar cells is tuned to just a narrow band gap of light, a narrow set of wavelengths of light, and then you stack them all up, and you can collect more efficiently the entire solar spectra. And that's what multi-junction solar cells are attempting to do. Now, the most current generation of space-based solar cells are actually up to like 5 junctions. So they can take the solar cell efficiency up to 38, 39, almost 40% today in the lab, which means in the next 5 years, those cells will be commercially available for space-based applications, and you'll see solar cells with 40% efficiency. Now, and as soon as we can make them cost-effective, then we'll see them in terrestrial applications. And it turns out the methods that are being explored are commercially viable to do that. And there are at least a couple existence proofs in the world of that in commercial efforts, one at Alta Devices and the other at a company called Microlink. Does that help? I'll take that as a yes.
The other questions, I guess, is probably a good time to get caught up on some of the questions that come in.
Yeah, please.
First off, are you willing to share your slide deck?
Yeah, happy to. There's nothing proprietary in any of this. This is all public domain.
Okay. Here's another question here from Sami that just came in. Flexibility. Well, I should just read it verbatim. Flexibility concerns only for PV cells or including the silicon substrate, and any ideas or suggestions in amplifying the power drawn? So I guess.
Can you read the first part? Yeah. I missed the first part of the question.
Yeah. I think it means, is flexibility concern only for PV cells, or does it include the silicon substrate? Sami, I'm not sure I understand the question. I understand the second part of the question. Do you have any ideas for amplifying the power drawn?
Yeah, I mean, well, amplifying the power, the only way you can amplify the power of a solar cell is to pump more light into it.
Yeah.
And so, there are various kinds of films that can be applied to solar cells that will attempt to create a concentrating factor of the sun's energy onto the cell. But you know, they don't produce a tremendous benefit. You know, you might see in a thin film form, you might see 15 or 20% more light hitting the cell. Now there are other commercial applications for concentrators where they take, you know, hundreds of times the sun's intensity and focus it onto a small solar cell. And you know, certain of these solar materials can be designed to accommodate that and directly convert that energy, and you'll see much higher efficiencies. So you'll hear about solar efficiencies of concentrating solar systems of over 40%. But what they're doing is they're using, you know, these high efficiency 30% cells, and then they're putting 1,000 suns of light on the cell, and the cells are size of postage stamps, and they concentrate. There's big lens concentrators that concentrate the sun's light. So really, that's the only way you can increase the power output ultimately, is to increase the amount of energy input via the sun that you're getting onto the cell. Now, there's lots of things you can do to optimize the performance, but beyond this kind of theoretical limit, you know, there's nothing you can do to increase the power other than having more light input. Do you have other questions, Mike, or should I continue?
There is one. I'm wondering if you have it later on. There are questions around the practical. Which one of these do you recommend? Like, for instance, Mark was asking of the commercially
well, I'm a little
available
biased in that I worked for 4 or 5 years for a gallium arsenide solar cell company. I mean, from my perspective, just speaking honestly, the only option is a thin film, high energy density material that's really lightweight. So you want to pick the lightest weight one. For most of these applications, because you know the aircraft are small, the cost is not going to be a major concern. You know, and I'll show you a few of the public efforts at the end of the deck here, illustrating what's possible with a couple of the materials, and I'll point out, you know, what really is going on there in the background of those two efforts. But you know,
so Joe, quick time check. I know you have
the best choice by a long shot.
Okay. Quick time check for you. I know that you've got a hard stop at 55 after. How many slides do you have left?
Just a few slides left.
Okay.
Yeah, there's just a couple slides left.
Cool. All right. So the recommendation is the gallium arsenide.
Okay. Yeah, gallium arsenide definitely what I would recommend, and I would definitely look at it in its thin film form. That's, you know, and the figure of merit here is this, just the energy density, the power density here. You know, there is no other material that approaches 1,000 watts per kilogram, and can do it in a really thin form. And you know, the practical challenges of trying to integrate a rigid silicon cell are just really, really hard. And as again, you know, they only lend themselves to large aircraft where there are gentle bend radius. Then you can apply them. So I have a couple more slides.
Axel actually has Axel actually raised his hand. So I'm gonna unmute you if you want to quick ask a question. And Axel, we can hear you if you're on. All right, Axel, if you want to just shoot me a message too, we'll get your question in. All right, no worries. Put him back on mute.
Okay.
Okay, as you were, sir.
Okay, so just to summarize in the comparison, you know, that today the best commercially available material is clearly the monocrystalline silicon. The thinnest cells are about 130 microns. The existence proof of their use is with the solar impulse aircraft, the Swiss effort, manned aircraft. Lots of public domain information on, you know, that airplane and how they do what they do. That cell has a engineered back polymer film which supports it for bending. So the cell's 130 microns, and then there's another polymer which is probably another 50 or 100 microns, which helps the cell stay intact during bending. And so the actual laminate is thicker than 130 microns. Thin films are your best choice. Amorphous silicon and SIGs, they're on metal foil or on glass. Cadtel is only on glass. That's the first solar technology, US-based thin film company. Gallium arsenide thin film is done on a composite substrate, so it can be very light. The composite is basically an inexpensive plastic and a thin back metal. It's largely copper in all cases. SIGs and Cadtel are encapsulation challenged. Environmentally, both of those materials are susceptible to moisture incursion, so you have to take great You have to go to great efforts to seal the material for moisture incursion. And so, even just common PET films are not good enough to cover SIG cells. They will absorb moisture rather quickly, and you'll see a dramatic degradation in performance. The material does not like to be hydrated. Amorphous silicon and gallium arsenide are completely inert to environmental condition, moisture in particular. In both cases, you could dunk these cells in water, shake them off, and they'll work just fine. You do worry about the corrosion of metal conductors, but the semiconductor material is largely inert in both cases. A few things to think about on system design. You have to string all these individual solar cells together in some way, and there are largely three methods to do that. You could interconnect the cells in strings and connect those strings in parallel. That's a series parallel. That's diagram A there. And so as you connect each of the cells together, you're building voltage. Each of the cells has an open circuit voltage, a voltage when it's not connected. And then when you string them together, it's like you just add them together and you build a voltage for the panel. As you string more strings as you take more strings and put them in parallel, you start building more current into the panel, and the power then is a result of the current and the voltage. There's another way to do that. It would be this, what we call a total cross tie. And so this is basically massively parallel interconnect while having rows of cells that are going to be serially connected. So you can build voltage and current simultaneously. There's some advantages to this interconnect, which I'll try to highlight in a second. And then there are variations on that to those two concepts, which can be used for different reasons. The reason why you look at these different layouts is, these cells behave differently when they're put into a system, and you worry about certain things when you put solar cells into a system. Largely, we worry about what's known as breakdown voltage. And so the breakdown voltage is basically a threshold at which if the cell sees a voltage that's higher than that, the cell will start to break down. It will start to degrade, and current will try to flow in the wrong direction, i.e. this reverse bias. So when current tries to flow in the wrong direction of a cell, the cell puts up a fight and it dissipates energy in the form of heat, and that resultant heat can damage the cell permanently. And so we then have to integrate things like bypass diodes in the array, in the interconnect of cells, to guard against that. Having a massively parallel interconnect, the series or the cross-tied interconnect, eliminates the need largely to integrate more diodes. Now, some of these solar technologies lend themselves much easier to that kind of interconnect versus others. Crystalline silicon cells are designed to be strung together in a series parallel form. They don't like to be cross-tied because the cells don't have a commercially available interconnect structure to do that. The gallium arsenide cells accommodate that completely. And so we find that there's a big benefit to being able to do this kind of massively parallel cross-tie interconnect. And largely it's for two reasons. One, we don't have to integrate a bunch of diodes into the device, so into the panel. So the electrical complexity is reduced dramatically, so the integration is much easier. And second, whenever the panel sees shadowing, if a series of cells are shadowed and they're in a string of cells, that whole string will lose power and it will become inactive because all of the cells need to be conducting in order for that string's power to be contributed to the parallel string array. And so if one cell or one series of cells becomes shadowed, which can easily happen as an aircraft orbits, the wingtips have dihedral, as you turn away from the sun, you can imagine the wingtip puts a shadow on part of the array. If that happens in a series parallel interconnect, you'll lose all the cells that are in that string, not just the cells that are shadowed, but all of the cells that are in that string, and so the power drops dramatically. In a cross-tie interconnect, you only lose the power that's generated by the cells that are shadowed. And so in a dynamic case where something's moving, You want an interconnect that's shadow tolerant because you'll collect a lot more energy over the duration of the task. And so, you know, anybody that wants to go deeper on this, I'm more than happy to talk to you offline about it. But you want a technology that allows you to accommodate shadowing, and you need to be thoughtful in the design about understanding under what conditions the cells are going to be shadowed in the operation that they're going to be in, and you know what can you do to configure the array to mitigate that problem. Okay. Now again, these cells are all strung together one way or another, whether it's cross-tie or series parallel. They're put together to build voltage into the module. And largely, you want to build a module or an array of cells that has a voltage that's close or near the operating voltage of the system. And usually that's determined by, you know, what the motor is running, what voltage motor have we chosen. In the case of some of these technologies, you can build voltage very quickly. And so in a very, you know, narrow chord of a wing, or in a panel of a wing, you can, you know, build the voltage up quite fast. Other technologies you can't. In the case of silicon cells, you're tied to this kind of large form factor cell, and each of the cells is 0.65 volts. So if I want to get to 10 volts, I have to string together, you know, 17 cells or something. So I take up a lot of area in a string to do that. You know, gallium arsenide cells, on the other hand, are 1 volt open circuit in their single junction form, and they're over 2 volts in the 2 junction form. So one of the advantages of these 3-5 materials is that you can build voltage very quickly in the array, and you can, you know, run at higher voltages, which allow you to really align better to the needs of the aircraft. And that's important. Being able to, you know, get to the right operating voltage is important because it opens up a lot of options at the system level. And I'll try to, you know, identify this in the last couple slides here. I already spoke about bypass diodes, so I'll skip that. But, you know, and ultimately what a bypass diode does is it just allows energy to be dissipated in the diode as opposed to being dissipated in the cell. And, you know, that preserves the integrity in these shadowing conditions. And again, there are a number of considerations for the location and number based on the size of the array. But ultimately, I think what's important here is that, you know, for these applications, is that you design the array to be very close to the battery that supports the motor. You know, most of these small UAS systems are going to have anywhere between 12 or 30 volts of system voltage, depending on, you know, what battery you're using. Like a 3S lithium-ion cell is like 11.8 volts nominally, or 12 volts nominally, something like that. And so you want to have a solar array that is just slightly above that voltage. If you do that, then you can literally, you know, basically connect the solar panel in parallel with the battery, put a single diode between the battery and the interconnect, or excuse me, the solar panel and the interconnect, and you can just pump the power right into the motor directly. Or you could charge the battery directly, depending on what kind of battery it is, and forego the need for a charge controller and an MPPT controller, which are complex electrical hardware that is, yes, it will condition the energy to where you need it if you can't get it there by just configuring the array correctly. But it adds complexity, it adds cost, and it ultimately reduces the overall system efficiency because each of those components has some loss associated with it. And so, you know, these are all considerations. Now, you could go for hours about how these things are designed, but just generally, you want to be able to design a system that's going to be close to the target operating voltage, and several of the options allow you to do that easily. Several don't. I listed a website that's of use for folks that, you know, manage small UAS projects. Castle is a company that builds all kinds of components for, you know, small aircraft. They have a flight calculator application that lets you input all the characteristics of the aircraft, lets you pick the commercially available motors, the controllers, the batteries, and propellers and all that, you know, geared systems, whatever the drive system is. It allows you to model it there, and it will tell you what you should expect in terms of flight performance, duration, allows you to, you know, theoretically set the throttle position wherever you want. You can, you know, model the system completely on the ground. and that'll help you determine what your real power needs are and what the power consumption profile is. Then we can look and overlay the generation profile of a solar panel onto that, and you could see precisely what will be the benefit. And I'm going to skip the next slide and just skip to this best effort. You could model precisely, an aircraft just like this. This aircraft is the AeroVironment Puma. I don't know, there are a couple thousand of these that are used by U.S. military, also Coast Guard. It is one of only 2 aircraft in the U.S. that are approved for commercial use in a small UAS category. The other one being Boeing's Scan Eagle. And this is the only 2 aircraft that are certified for commercial use in U.S. airspace. This particular aircraft, outfitted with 125 watts of thin film gallium arsenide cells by Alta. We added about 4.5 ounces of weight. These cells, because they're so thin and lightweight, they can actually be integrated right into the laminate that is the aircraft layup. So this is a fiberglass composite aircraft. It's got basically a foam wing core with a fiberglass skin that is molded. It's compression molded at temperature. And so the way this was built is they wet the mold out with epoxy, and then they lay the solar arrays in there. They're just like paper, very thin, 100 micron thick solar film of interconnected sheets of cells. They lay that in the mold, and then they just put the fibers and do the rest of the layup on top of that, clamp it shut, cure it, and pop it out of the mold, and you get this fully integrated bonded solar panel without adding any additional adhesives or laminating films to protect the solar film. And so we just added literally 4.5 ounces of weight and put 125 watts of power available on that aircraft. If you go to their website, and the aerovironment.com website, you can see the results of their flight. This aircraft normally flies for about 90 minutes under battery power, and we demonstrated on a day in November a flight of over 6.5 hours, so that was kind of winter solstice, and then a flight in July near the summer solstice on not a particularly clear day. We flew for 9.5 hours and were able to demonstrate we could have flown continuously from dawn till dusk and into the evening, probably a good hour. The reason we landed out was due to darkness. And so, you have a proof of.
Hey, Joe, you're coming up on time here. We got 2 minutes till 9. Do you have any closing statements on kind of your like the summarization of kind of what you're?
Yeah, I guess my summary is this. The practical application of these materials in the aircraft, you're really driven to some really defined attributes: lightweight, flexibility, thin, high energy density. You want to optimize all of those. You want to pick the material that delivers the best in all those regards. The best available option today are thin film gallium arsenide devices. They're available through a couple sources. As those companies become commercially successful, we expect to see more and more competing efforts and more material availability. Their costs today, I think, can largely be intercepted and found useful by efforts like your own. They don't seem to be cost prohibitive for most of the efforts, certainly not for military use, but also for commercial uses. They can prove to be economic. And I think that the impact of being able to triple or quadruple the flight time of a small UAS, critically important. It's not just about duration, it's about range. If you can spend 3 hours ranging out to a target and 2 or 3 hours dwelling on it and 3 hours back, you've increased the utility of that aircraft immeasurably. It's not just about being able to fly within eyesight for an extra 30 minutes, but being able to really range out, I think, is the benefit. That's it. That's all I have.
Excellent.
How can they get a hold of you?
Yeah, there's resources.
Sorry.
How can you reach me?
If anybody want to get a hold of you, how could they? Or
you can reach me on my. No, I'm happy to answer any questions that any of the members might have and to collaborate with them to my ability. You can reach me at jwfoster@yahoo.com. That's my private email. and just shoot me an email, and I'll respond as quickly as I can.
So jwfoster@yahoo.com. You beat me to the punch.
That's right. And then, Aaliyah, I could just make available to you the materials from today, and if you distribute them how you see fit.
Okay, great. Yeah, well, thank you so much. We really appreciate your time and giving us an opportunity to learn more details about the materials and the applications, because I think that's a very important component. Just understanding what solar cells are is one aspect, an overview, but actually how and what are the materials that are available, who produces them, how do you actually apply them in the best format, is very useful for, I think, not just our teams, but other people around the world that are looking at solutions using solar powered UAVs.
Well, thanks for having me today. Appreciate it.
Thank you. Mike?
Brilliant. Joe, thank you. That was very informative. I mean, I learned a lot. I actually had some experience in solar, so this is good stuff. So thank you so much for your time today. And with that, everyone, we'll see you on the next one. Which, Leah, real fast, what are the next ones coming up?
Actually, yeah, that's what I was just going to send you guys a link. There's actually a webinar we're hosting this coming Sunday. It's actually a really interesting one. It's being done by a guy named Jeff Hooper, and he actually just won an Oscar award for science and technology using for his aerial filming at the LA Oscars this past February. So it's exciting. He's actually going to come on and he's going to talk about the best practices of Sorry, I muted myself instead of you, Mike. But he's going to be talking about what are the best practices of aerial filming, especially for surveillance purposes. But then he's also going to give our teams some tips on how do you, as teams, record your progress. So for the final documentary that we would have for the WCUAVC, we can incorporate bits and pieces from different teams that have been recording their progress during the next few months. So that's going to be an important part. So if you guys have any of your team members that are available, we usually don't do our webinars on Sundays, but for Jeff, on Sunday worked much better. So that's why we're holding this particular Sunday at 2 p.m. So the time is different than our normal time, which is 11 a.m. Eastern time. It's 2 p.m. Eastern time, which I think is a 6-hour difference to South Africa. So figure it out, guys. It's available. I sent the link to everybody that's interested in participating. And then next Thursday is the one everyone's been waiting for. It's on RFID tags. We have our expert who will be talking about it, and he will also be the person that would be facilitating the RFID tags for the final competition in November. One last thing from me is I'm really, really excited. Next month we have the AUVSI conference in Orlando, Florida. So I will be going there and learning as much as I can about what's available right now and coming back and giving you guys feedback on what we learned and what we saw, and hopefully pick up some really good people that would be interested in doing some webinars for our teams as well. So that is the week of the 11th of May. So right after I get back from the AUVSI conference is our leadership and team member webinar that we'll have on the 17th or the 18th of May. So I'll see you guys on that. You'll have open access to asking questions, and for me to share my experience at AUVSI this year compared to last year in August. So looking forward to that. Thank you again for participating. And Mike, you're our closer.
All right, guys. I'll leave it at that. See everyone on the next. Take care, guys.
Take care.
Bye.
Ciao.